Yeah, good morning all. So in the last class, we looked at non-determinism, some differences between non-deterministic finite automata and deterministic finite automata, right? Three major differences. In DFAs, there is exactly one outgoing arrow for each input symbol, no more, no less. In NFAs, there can be 0, 1 or many outgoing arrows for each input symbol. And second thing, in DFAs, epsilon cannot be an input symbol. Only the symbols in the alphabet set can be the input symbols. Whereas in NFA, epsilon can also be an input symbol or a symbol on the arrows. All right, but epsilon is not part of the alphabet set. It is separate from the alphabet set. Still, it is allowed in NFAs. Okay. And the third thing, in a DFA, since there is exactly one outgoing arrow for each symbol, you always map only to one state. If you are in a particular state and you get a particular input, you go to one particular state, one output state. Whereas in NFA, since there can be more than one outgoing arrows or there can be no outgoing arrows for a particular symbol, for a given state and an input, the output is not one state, it can be more than one state, right? So it is a set of states, or it can be no state also, so it can be an empty set also. Okay, but the point is it is basically a set of states. In NFA, the output is a set of states, whereas in DFA, the output is one state. So these are the three major differences between DFAs and NFAs. And then some other points that I mentioned, NFA is no more powerful than a DFA. Both are equally powerful. Then why NFA? The only reason is NFAs are more convenient than DFAs. That's all. They're not more powerful, but they are more convenient. They are easy to construct. They are easy to understand, and they have fewer number of states, right? But in terms of power, NFA and DFA are equal. Every NFA can be converted to an equivalent DFA. Every NFA has an equivalent DFA. Okay. And another thing, NFA can be thought of as parallel, many DFAs running parallelly. Okay, it can be thought of as parallel computation. It's because for any given input, say if you are having two or more arrows, you can think of it as having or taking two or more branches at the same time. So I can go either in this direction or is this direction, or I can take this branch or this branch. So I'm basically simulating two paths or two or more paths at the same time. I'm testing out this path also, this path also, this path also. I'm testing out multiple paths at the same time. If at any one of these paths, if I land up in an accept state, then I can say that this string will be accepted by this NFA. So you can imagine it's like a tree, and this tree has branches. If in any of these branches, if I end up in an accept state, then the string is said to be accepted by the entire NFA. So we looked at such an example. So this is an NFA, right? And then we took one particular string, this one 0 1 0 1 1 0, to see how this NFA would be simulated. All right. So it can take more than one path. So it will be like a tree. This is called process tree. This tree is not NFA. The above one is NFA. This is the process which NFA takes on one particular string. That's all. Okay. So it's like, say, you start with Q1. If you get a 0, you go to Q1 only. There are no more outgoing arrows. All right. And then you are again in Q1. Now you get a 1. The next symbol is 1. Now the machine tells us that I can either go back to Q1 or I can go to Q2. On input 1, I can go to Q1 or Q2. Now there are two possibilities. So I will try out both the possibilities at the same time. All right. So Q1, Q2, but why Q3 came? Because from Q2 to Q3, there is an epsilon arrow. Epsilon arrow means the moment you enter Q2, you can also enter Q3 freely without reading any more input symbols. All right. So since from Q1, you are able to reach Q1 and Q2, you are also able to reach Q3. Okay. So whenever you have an epsilon transition, whatever previous state, whenever you're able to enter the previous state, you can also enter the next state with epsilon transition. So immediately put that state also along with the previous state. So Q3 comes freely. along with Q2 whenever you enter Q2. Okay, so wherever you arrive at Q2, you also should write Q3 because there is an epsilon transition between them. Okay, so now you have three possibilities: Q1, Q2, Q3. In each of those branches, you should test with the next symbol. The next symbol is 0. Okay, so now Q1 again goes to Q1 on 0. Q2 goes to Q3 on 0 according to the machine. Q2 goes to Q3 on 0, right? And Q3 goes nowhere. Q3 does not have an outgoing arrow on 0. So you need to assume whatever arrows are missing, they are all going to some invisible dead state, which means the computation does not proceed further. There's no use in even proceeding further. You know you're going to a dead state and you're not going to come out of it, so you need not waste your time pursuing that path. All right, so you can ignore this path. So Q3 does not go anywhere on 0, so you can ignore this entire branch. That will become a dead branch. You pursue the remaining branches. Okay, so Q1 goes to Q1 on 0, Q2 goes to Q3 on 0. The next symbol is 1. Now Q1 goes to Q1 and Q2 and Q3 also, because there is an epsilon transition between Q2 and Q3. And Q3 goes to Q4 on 1 according to the machine. Now the next symbol is 1. Again, Q1 goes to Q1, Q2, Q3 on 1. Q2 goes nowhere because there is no outgoing transition for Q2 on 1, right? You see, Q2, there is no outgoing transition on 1. So that becomes a dead branch. And Q3 goes to Q4, and this Q4 also goes to Q4. And so on, you proceed like this. Finally, you will end up, by the time you are done reading the string, this string has 6 symbols, 0, 1, 0, 1, 1, 0. Now you are done reading the string. Now you are left with some leaf nodes in the tree. If at least one of those leaf nodes is an accept state, that is enough for you to say that this string will be accepted by this NFA. All leaf nodes need not be accept states. Just one leaf node needs to be an accept state. All right. So that is enough for the string to be accepted by the NFA and in turn by its equivalent DFA. All right, that's all. Okay, in this case we have an accept state. We have two branches ending in accept states, so this string will be accepted. Okay, so now let's work out some examples of NFAs. So far you have constructed DFAs. Whatever finite machines or finite state machines you have built, those are all DFAs. Implicitly, although I didn't mention explicitly, they are all DFAs. Now let's build NFAs. So try to build an NFA for this language. Construct an NFA, say N2, which recognizes the language L, which is a set of words or strings where each string has 1 as the third last symbol. And the alphabet set is 0, 1. Okay, so for example, say if you have a string like 1, 0, 1, 1, 0, this will be accepted because the third last symbol is 1. And say you have another string like 1, 1, 1, 0. This will also be accepted because the third last symbol is 1. But if you have a string like say 1, 0, 1, 0, this will not be accepted because the third last symbol is 0. Okay, so before and after any symbols can be there, but the third last symbol has to be 1. That's the only condition. So all such strings, so build a machine which accepts all and only such strings. Okay, third last symbol should be 1. That's all. Is everyone done? Okay. Anyone else? All right. So let me move on to the next page. Yeah, you tell me. How many states are there? Okay. Zero, one, and epsilon. You don't need epsilon for the self loop. It will. That will be accepted. Hmm. That's it. So is this right? Hmm? No. What should I change? For one, it will be it will go to Q1 and Q2. It's done. It's there. No 0, 1. It's going to Q1. That's enough. You will send it to both. It's not a either or thing. It's both. It's not like you should decide where do you send it to. Wherever it is going to, the outgoing arrows are there. You will send it to all those places and try out all those options. And one of those options may work, some other option may not work. That's all. So is this right or not? It's correct. See, it's quite simple. Yeah. Yeah, that's all. So basically, all you need to worry about is the third last symbol, right? The ones after that can be 0 or 1, and the ones before that can be 0 or 1. Any number of zeros and ones can come before, but after that only two symbols can come, and maybe either 0 or 1. All right. Now, what if I put, say, some self loops like this? Here also I put 0, 1. Here also I put 0, 1. What will happen? Yeah, one thing is there can be many more symbols after this one. I cannot be sure that there are only two symbols after that one, right? Which means I cannot be sure that this is the third last symbol, right? So there can be any number of zeros and ones after that. So even a string like 0, 0, 0, 1, this will also be accepted, because say here I'll have three zeros and then a 1 here. This will be accepted, but this should not be accepted, right? So I should ensure that there are exactly two symbols after the 1. The last, the third last digit, there should be exactly two symbols after that. All right. Okay. Now, the point is, how do I know this is the third last symbol? There is no way, because I cannot see the end before it comes. I can only see the current symbol, and I don't know how many more symbols are remaining. So all that I can do is I can assume maybe this is the third last symbol, maybe this is not the third last symbol. All right. So I will take both the paths. I will run both the paths, both the branches parallelly. That is why this Q1 goes to Q1 on 1 and also to Q2 on 1. If it goes to Q2 on 1, it is basically assuming that maybe this one is the third last symbol. Okay. And I will get only two more symbols after this. So I'm assuming that this one is the third last symbol. That is one branch. The other branch is, what if this is not the third last symbol? Right? So let me keep a backup. I will stay in Q1, right? And wait for the third last symbol. Okay. Again, in next branch, I will again assume that is the third last symbol. and I will take that branch. But I will also again keep a backup. Maybe that is not the third last symbol. I will continue in this branch. Again, I will take one more branch. Maybe this is the third last symbol. So for every symbol you see, you assume that is the third last symbol and take a branch. Again, for the next symbol, you assume that is the third last symbol and take a branch. Again, for the next symbol, you assume that is the third last symbol and take a branch. Only one of these branches in this particular example, for this particular machine, only one of these branches will end in an accept state if the string is valid. If the string is not valid, none of the branches will end in an accept state. But if the string is valid, only one of the branches will end in an accept state. Okay, so let's try that out. Let's look at the process tree of one particular input string. All right. So let's take a string like say 0, 1, 1, 0. Is this a valid string? Yes, because the third last symbol is 1. All right. So let's test it out. So suppose I start with Q1 and my input symbol is 0. So Q1 on 0 goes to only Q1. Okay, so no branching there. Because there is no need to branch. I only need to worry about if the third last symbol is 1. If it is 0, I will assume that it is not the third last symbol. So I need not worry of branching out at that time. All right. So Q1 goes to Q1 on 0. Next symbol is 1. Now Q1 goes to both Q1 and Q2. Right. So it takes both the branches, Q1 and Q2. So what does this mean? This branch means what? Q1 going to Q1. What does that branch mean? Yeah, it's assuming it is not the third last symbol. Okay, so maybe it will come later. So let me wait for that. So again, I'm going to Q1. Again, I'll wait for the next symbol, assuming that is the third last symbol. All right, but I am also taking Q2, assuming this particular symbol is the third last symbol. So I'm making both the assumptions and I'm taking both the branches. One of these assumptions has to be right. Right? That's all. Now again I get a 1. Now this may or may not be the third last symbol. Right? So I will, when I'm in Q1, again I will take 2 branches. Assuming this is not the third last symbol. And assuming this is the third last symbol. In Q2, I can't make any more assumptions. I have only one path to take. The moment I'm in Q2, I sort of already assumed that this is the third last symbol. So I am left with only 2 more symbols to read. I can't take any more branches there, right? So I am in Q2. I read a 1. I go to Q3. All right. Okay, before I proceed further, which of these branches do you think will end in an accept state? The right one, this one, right? This branch will end in an accept state. Why not this branch? Because it came a bit late, right? It is actually considering the second last symbol as the third last symbol. So this will not end. This will end before it finishes reading the string. Okay. So you should take the right branch and also at the right time. You can't be before or later than the correct position. All right. Here it branched out at the exact same time because this is the third last symbol and it assumed this is the third last symbol at this position. Only this branch will go to the final state. But this is not the third last symbol, but it is assuming this is the third last symbol here. So it will not work out, right? All right. So the next symbol is 0. Q1 on 0 goes to Q1. Q2 on 0 goes to Q3. Q3 on 0 goes to Q4. Okay. So Q1 on 0 goes to Q1. Q2 on 0 goes to Q3. And Q3 on 0 goes to Q4. That's it. We are done reading the string. No more symbols are left. Now, are there any accept states in the leaves? Q4, right? So this is an accept state. That's it. So this string should be accepted. All right. Now, suppose I have one more symbol, maybe 1. All right. Now, which branch will be an accept branch? The middle one. This branch will be an accept branch because this will finally again end in Q4 and this will be the accept state. Here Q4 will not go anymore after 1 because it gets stuck. It can't read any more symbols. It goes to dead state. All right. So this branch will be discarded. All right. So that's the whole thing. If you are branching out at the exact position, that branch will work. All other branches will be discarded. In this particular example, in the previous example, more than one branch ended in the final state, but in this example, only one branch ends in the final state always. Okay, so that's the thing. Okay, so 0, 1, 1, 0 will be accepted by N2. All right. Okay, so now for the same language, try to build a DFA. We built an NFA. Now try to build a DFA for the same language. That the last third symbol should be 1. Yeah. Q4 will not become a leaf node. That will be discarded. Leaf nodes are those which are left after reading all the strings, all the symbols in the string. So try to build a DFA for this.
Get an accept state, the leftmost node, like very late. Will the machine compute all the accept states, or they just get one accept state and it ends the exit?
It's up to us. It's like imagine you are running parallel computations, and like parallel computers, you are running this on parallel computers. You can make a rule that if at least one of the computer is done processing, give me an indication and I'll stop all the process. That's all. Is anyone done? See, one way to think of it is first try to think of in terms of writing a program, be it C, Python, whatever it is. If you are trying to write a program to solve this problem, how would you do it? Like you should write a program which takes a string, and if the last third symbol is 1, you should print yes, otherwise no. How will you solve this problem? Yeah. You see, one way of solving it is there are multiple ways. One is suppose you don't have any limit on the length of the string that you can store. You can store a string of length 1 million, 1 billion, or your array size is whatever. It will always be bigger than the string you are reading. Then the simple thing is you read the entire string and then just check whether the last third symbol is 1 or not. That's one way. But suppose I don't have such an array. All right. Now, there are two ways. The first way is like an NFA where you write 3 levels of if conditions, right? Like assuming, say, if the current symbol is 1, and then you go to the next step. If there is one more symbol, 0 or 1, and then next step, there is one more symbol, 0 or 1, and then the last step, if the last symbol is null, okay, then accept. Fine. But the point is, you don't know, like there are only 3 levels, right? But you don't know where to put the else condition. So this is actually the NFA which we saw earlier. The only thing is, you should keep running such NFAs, these programs, parallelly for every next symbol you read. Okay, so currently say I have a long string 0 1 1 1 0 0 0 1 1 1, something like that. Okay, so what you should do, you take this symbol, run this program, then you take this symbol, run this program, then you take next symbol, run this program. So for each symbol you should run this program. So you should run many parallel programs. This is what NFA is doing. All right, one of these programs will land up in an accept state or a reject state. It's like one of these programs will print yes or no. That is the program where you are actually reading the last third symbol. Okay, otherwise you don't know when you are encountering the last third symbol. Fine, this is like NFA part, the equivalent program for NFAs. DFA's corresponding program will be slightly different. So there, in this case, are we using any memory? Are we using an array? No, we don't need to use any array. All that we are saying is read the current symbol, then read the next symbol, then read the next symbol, and then read the next symbol. So we are saying read the current symbol, read next 3 symbols. All right. We are not storing because we are using the if conditions. The moment I come into this if condition, I know the previous symbol is what. It doesn't matter. I did not store that. All right. But there can be an option where you can store symbols. Now, what is the minimum length array you need? And that is both minimum and maximum. How many symbols you need to keep track of? Yeah. How many? 3. Yeah, just 3 symbols. So that you know the last third symbol at any given point of time. And if you know you have done reading a string, whatever is the last third symbol in that set of 3 symbols, if it is 1, you print yes, otherwise print no. Okay. So now when you are translating this to a machine, now can you guess what will be the states in this machine? The states in this machine are nothing but the states of this array. This array, which stores 3 symbols, in what all different states can it be in? How many different states can it be in? How many different sets of 3 symbols can you get for 0 and 1? 8. 2 into 2 into 2. That's it. You have 2 possibilities in the first place, like 2 possibilities in the second place, 2 possibilities in the third place. So 2 cube, 8 different series of zeros and ones times 3 you will get. This is exactly why using 3 bits you can represent 8 numbers. This is exactly why using 8 bits you can represent 256 different numbers. Why? Because 8 bits is what? 2 into 2 into 2 and so on up to 8 times. That is 2 power 8. Because each bit can be either 0 or 1. So 2 possibilities, 2 possibilities, 2 possibilities. You multiply 2's so many times as the number of bits. You will get 2 power number of bits. That will be the total different possibilities that you can represent using those many bits. So since you have 3 bits, assuming here it is a bit, the array, each cell is a bit. You have 2 possibilities in each bit. So 2 into 2 into 2, 2 cube, 8 different numbers you can represent. So those 8 different numbers will be the 8 different states in the machine. And each state represents the last 3 digits or the last 3 symbols that I have seen. Right? So I will land up in, if I land up in any of those states where the last third digit is 1, I will accept the string. If I land up in a state where the last third digit is a 0, I will not accept the string. Right? So how many accept states will be there out of these 8 states? Why 4? Yes. That's it. See, there are 8 states. Out of those 8 states, 4 of them will have third last digit as 1. 4 of them will have third last digit as 0. So any of these third last digit, any of these states which have third last digit as 1, they will be accept states. The remaining will be non-accept states. It is basic, simple, common sense. And I see that it is lacking among most of you. I think even a school kid will say this, but BTech students are not able to say this. Anyway, so let's proceed. Okay, so we have 8 states. So rather than saying Q1, Q2, Q8, let's name them so that their meaning is reflected. So Q000, Q001, Q010, then Q011. So these are all the states where the third last digit is 0. And then remaining 4 states where the third last digit is 1, that is Q100, Q101, Q110, and Q111. All right. Now, what are the accept states? The second row. All these states are accept states because their third last digit is 1. Okay. Okay. What is the start state? What should be the start state? Sorry, another state. What should I say? Q. If it's 0, it goes to Q000. If it's 1, it goes to sorry. It can take epsilon also, but what should that state be? And why do we need an epsilon transition? Epsilon is not an element. Epsilon will not be part of input in the sense it's not part of the string. You will use epsilon when, say, without reading any more symbols, you want to go to the next state. First of all, this is DFA. Here, epsilon will not come. Epsilon will not be a label on any of the transitions. So that is something you should keep in mind. Epsilon will not be a label on any of the transitions because this is DFA. Only NFS will have that. Okay. So what is the start state? What should be the start state? Yeah. Q0 or 1. What do you mean Q0 or 1? So should I have two states, Q0, Q1? It could have like this 0 or 1. No, you can't have such a state. That state's meaning should be unambiguous. You can't have an OR condition within a state. Sorry, Q what? Q01 on 1 it goes to Q000 on 1. Why?
So 0 will be a self group around 1 and go to 1.
For what? Which state?
1 will be like a Q0.
And
self group 0.
Okay.
And then when you get 1, we go to 0.
Not something. Okay. See, technically speaking, you cannot enter any of these states directly because you need to read 3 symbols by the time you enter any of these states. But you can't read 3 symbols at a time. You read 1 symbol, then 2 symbols, then 3 symbols. So technically, you should have more states like, okay, Q, where I haven't read any symbol. And if I read a 0, I go to Q0. If I read a 1, I go to Q1. Okay. Now again, after reading 0, if I read another 0, I go to Q00. If I read another 1, if I read a 1, I go to Q01. And if I'm in Q1, if I read a 0, I go to Q10. If I read a 1, I go to Q11. Right? Now, if I read a 0, I go to Q000. If I read a 1, I go to 001. Right? And here, when I'm in Q01, if I read a 0, I go to Q010. If I read a 1, I go to Q011. And so on, right? You can add like this, but this is not necessary. You can do away with them. Even without them, you can use the machine. And like I said earlier, if you can do away with some state, you don't include that. Try to minimize your machine as much as possible. All right. It is like saying, suppose if I have state QA, which means I haven't seen a B so far. So one way is I am in QA and I have a self loop on A. Another way is I say QA and then I say QAA. Okay. And then I have a self loop here. but this is redundant. I don't need a separate state just to say the same thing, right? It doesn't matter to me whether I have seen 1A or 2A's or 10A's. All that matters to me is I haven't seen a B. So if I can do with this machine, I don't need this machine. Both are saying the same thing, but I don't need the second machine, right? Similarly, you try to, okay, let me do like this. So basically, technically, although these states may mean what are the last three symbols I have seen, you can overload the meanings of some of these states in the sense that, okay, I will assume that if I have read only one symbol or two symbols, I will assume that I will fill all the remaining gaps with zeros. Okay, so suppose if I read only one symbol, say that is 1, but I want to count 3 always, so I will fill the remaining gaps with zeros. Or suppose I read 1 1, I will fill the remaining gap with 0. Or suppose I read 1 0, I will fill the remaining with 0. I haven't read anything, I will fill it with triple zeros. Or I have read a 0, I will fill the remaining with 2 zeros. Or I have read 2 zeros, I will fill the remaining with a 0. Whatever it is, it does not matter to me because I am only concerned about 1. So until I see a 1, I don't care what the previous symbols are. Like exactly how we did here. You see, until I see a 1, it doesn't matter to me what symbols I have seen earlier. Okay, so I will just skip them. So now 000 may mean I have seen 3 zeros, or it may mean I have seen 2 zeros, or it may mean I have seen 1 0, or it may mean I haven't seen any symbol. All those meanings can be given to this state itself. Okay, basically 000 means I haven't seen a 1 so far. 001 means the current symbol is 1. The previous two symbols I don't know. I will fill them with zeros. 010 means the current two symbols are 10. The previous symbol I don't know. It can be 0. 011 means the current two symbols are 11. The previous symbol may be 0 or it may not be 0. Or I haven't read so far. There are only two possibilities. Either I have read 011 or I have read 11. That's all. So both those possibilities are getting covered here. Okay. But if I have read anything like 100 or 101 or 110 or 111, then I cannot skip them. I cannot assume that, okay, fill the third last symbol with something. No. Now I know the third last symbol is 1. The remaining two symbols can be anything, but the third last symbol is 1. So that state actually tells me what the three last symbols are. Okay. Even these states tell me what the 3 last symbols are, but they also play a role of helping me when I read less than 3 symbols. That's the only case. So only in the case where you haven't read a symbol, or you have read only 1 symbol, or you have read only 2 symbols, in these 3 cases, the top 4 states help you. Okay. When you have read 3 symbols, then all the states are equal. Whatever 3 symbols you have read, those 3 symbols are indicated by the state. If you have read less than 3 symbols, then fill the remaining spaces with zeros. So you don't need separate states where I have actually read a 0 or a 1 and then 01 or 011. I don't need like all the previous states I have drawn and erased. You don't need those states. Those roles can be filled by these states, top states. Okay. Once you reach the stage of having read 3 symbols, done. Now you need not worry about anything at all. Whatever 3 symbols you have read, you are in that particular state. The last 3 symbols are being indicated by the state in which you are in. So if I am in Q, say 010, it means I have read 010. The last 3 symbols are 010. That's all. Okay. So you need to put some thought. You need to reflect to understand what I said. Go back and reflect what I said. You don't need again individual states for 1 character, for 2 characters, and so on. You need not. You can reuse these states only for those cases also. Okay. So now this can be the start state, which means I haven't seen a 1 at all. The only state which satisfies that condition that you haven't seen a 1 at all is this. So I'm filling the buffer with zeros. Okay. Now, as long as you keep getting zeros, you stay in this state. The moment you see a 1, where do you go to? Yeah. 0, 0, 1. So basically, you always have a window of 3 symbols. Okay. So this is my window currently. If I get a 1, now I move my window to the last 3 symbols. That will be 0, 0, 1. Right. So if I have seen 000 so far, now I am seeing a 1, which means the last 3 symbols will be updated to 0, 0, 1. Okay. Now you have seen 0, 0, 1. Now you see a 0. Where do you go to? You go to 0, 1, 0. I am in 0, 0, 1. If I have seen a 1, where do I go to? 0, 1, 1. Okay, so let me erase this. I will go to 0, 1, 1. If I see a 1, okay. Now I am in 0, 1, 0. If I see a 0, where do I go to? 1, 0, 0. I am in 0, 1, 0. If I see a 1, where do I go to? 1, 0, 1. I am in 0, 1, 1. If I see a 0, where do I go to? 1, 1, 0. You discard this and append the next symbol. That's all. I am in 0, 1, 1. I see a 1. Where do I go to? 1, 1, 1. Okay. Now I am in 1, 0, 0. I see a 0. Where do I go to? I am in 1, 0, 0. I see a 0. Where do I go to? 0, 0, 0. I am in 1, 0, 0. I see a 1. Where do I go to? 0, 0, 1. Done. I am in 1, 0, 1. I see a 0. Where do I go to? 0, 1, 0. I am in 1, 0, 1. I see a 1. Where do I go to? 0, 1, 1. I am in 1, 1, 0. I see a 0. Where do I go to? I see a 0. 1, 0, 0. I am in 1, 1, 0. I see a 1. Where do I go to? 1, 0, 1. I am in 1, 1. I see a 0. Where do I go to? 1, 1, 0. I am in 1, 1. I see a 1. Where do I go to? 1, 1. Okay. So you see how complex the DFA is, right? How simple NFA is. Just 4 states, quite simple, easy to understand. But a DFA, it has so many states and so many transitions, and you need to keep track of so much information, right? So that's the difference between NFA and DFA. But both are equally powerful, both are equivalent. But NFA is more convenient. All right. So let's stop here.